Welcome back. Today we're going to be doing section 2.4, the precise definition of a limit. This is going to be a little weird, a little abstract in some ways. This is the beginning of proofs that you do in higher mathematics. So if any of you are going to be math majors, you're going to see a lot of this kind of stuff with even less letters and numbers, a lot more symbols and definitions and things like that. All right, so let's jump into the precise definition of a limit. So if we take our limit as x approaches a of f of x, and we have a limit L. And the way this is going to work is for any, or for all, and here's a new Greek letter, epsilon, bigger than 0, there is a corresponding number, and here's a Greek letter delta. This is where we get a lowercase, you can see this is where we get a lowercase d from, which is also going to be positive, such that, and here's the big payoff here. If we have 0, absolute value of x minus a, that's this a here, is less than delta, then the absolute value of f of x minus L, remember L is a y value, is less than epsilon. And what on earth does all of that mean? Well, let's talk about that. Let's say we have a function f of x. And we have our function, something just in general terms. So this is our f of x. So we're going to have a specific x value a. You can see specific x value. We'll put that right here, a. And what's happening is we are going to end up with some wiggle room just to the left and just to the right. And what we're saying is the distance away, and you can see what we're doing is we're squeezing these in. So we're approaching a from both directions. Remember, the limit has to be the same in both from both directions. And what we're saying is this distance here is a delta, and here's another delta. And what that's going to do is produce for us, and to be clear, this point right here is here at f of a. And then we have, I made these pretty darn similar. We'll see how this goes. I'm going to over-exaggerate this a little bit. And the distance that we're getting here, this is our epsilon. Same on the top one. That one's a little too small for me to write that in there. So here's what we're saying. If as we're getting closer and closer to a here, we should be approaching f of a here. Okay, f of a is our L in this particular case. So as this distance gets small, this distance should also get small in the same way. So let's rattle that around a little bit and kind of see what we're getting for that. So we're going to start here. The graph of a linear function f with the limit as x approaches 3 of f of x equals 5. So 5 is the limit L. For each value of epsilon, which is positive, determine a value of delta which is also positive, satisfying this statement that f of x minus 5, that's this here, f of x minus 5 in this case, is less than epsilon, if, and now we're to here, x minus 3 in this case, because that's the limit there. And notice it's a minus, so it's always the opposite sign of what you see there, is less than delta. So let's see exactly what we mean by that. And I want to point out that, and I'm going to make this a little more bold for us. So here's what we're looking to prove. And what we want to do is find a delta that's going to give us this statement here. Well, what we're going to do, and remember, these are y values. So we're going to go up 1. So we're at 5 here. We're going to go up here to 6. And down here to 4. So we're going a distance of 1. Right, 1 and 1. All right, and what we want to do now is see, now we're going to talk, so when we're talking about getting a delta, what we need to do is we need to, delta refers to the x values. So we're going to find the corresponding x values, which is right here. I went a little too far there. I should have gone just to the line here. All right, so this is giving us a total distance in the x direction. Do you see from 3 to 5, that's going to be a 2? And from 1 to 3, that's also a 2. Well, that tells us that our answer is that delta should be between 0 and 2 because of this here. Now we're going to do the same problem. So distance of 2 here, distance of 2 here. And here's our 1, 3, and 5. There we are. Let's redo it with this, except now what we're going to say is f of x minus 5 is now less than 1/2. Okay, once again, let's make it bold here. And here. And we want to go 1/2. Now, I don't know if you can see this, but the 1/2 is there, then 1, then 1.5, then 2, then 2.5, then 3, right, and so on. And so what we're going to do is we're going to go halfway up and halfway down. So this is 6 here, so 5.5 is there. So we're doing this. And 1/2 down here is here. And so this is a distance of 1/2 here and here. And what we're trying to find is how is that affecting the x values? Well, how far out are we going now? Now, notice this is a 1, that this is going to be 2, 3, 4. So notice now that has changed and has become a distance of 1 now. 1, a distance of 1. Which means our delta is going to have to go from 0 to 1 in this case. All right, I know this seems a little off, a little abstract. It's like, why are we doing this? How does this work? Let's try it again to see where we're going with this. So let's mark up again what limit we're trying to find. We're trying to find this limit here. And what we have is that we have g of x now, which is this kind of funky looking piece here. And we want to know the limit as x is approaching 2. So that's the x minus 2 there. And the limit L is going to be the 3. So there we are, g of x minus L, which is 3 in this case. Well, they're saying let's start out with epsilon equal to 2, which means g of x minus 3 is less than 2. Okay. That means I'm going to go a distance of 2 away. So if I'm here at 3 and I go down 2, I'm way down here at 1. And if I go 2 here, this is 4, 5. Which means I'm going way over here because this function is a little funky looking. All right. So let's go into the domain world, or the X world in this case. So how far away are we in the X direction? Well, we're 2 different distances, actually. For this one, we're a distance of 1. For this one, 2 to 6, we're a distance of 4. Well, that means what we're going to have to do is we're going to have to get the smaller of the 2. It's just the way it's going to have to work out. So this is my delta. So my answer in this case is going to be the 1 here. All right, we're getting there. Part 2, we want to find g of x minus 3 is less than 1 in this case. So a little less wiggle room. Let's map out once again what limit we're even trying to find. And now we're only going a distance of 1 away. So hopefully it's not going to be as exaggerated as it is here. But it will be a little. So from 3, we're going a distance of 1. And from 4, which is right here, distance of 1. So once again, and I forgot to mark this up over here, this was a distance of 2, a distance of 2. And now we have gone a distance of 1 and a distance of 1 there. So let's talk about in the X world now. Well, in one direction, in this direction, we're only 1/2. And for this one, this is 2, 3, 4. So we're here a distance of 2 from there to there. So we're going to pick the lesser of the 2, the 1/2. So delta has to be between 0 and 1/2 here. Hopefully that's not too confusing. I know it's a little awkward. You do a lot of delta epsilon stuff when you get into higher mathematics, get into something called real analysis. At least that's when a lot of it came out for me. All right, let's do some proofs. So the way we do a formal proof for this particular thing that we're doing now is we are going to first off find a delta that's going to work for our proof. Now our delta should depend on epsilon. So we're going to start here. So for this example, so just to be clear, A is 4 in this case, L is 1 in this case, f of x is 4x minus 15 in this case. So step 1. We're going to assume epsilon is bigger than 0. All right, so now we're going to do the absolute value of f of x minus L is less than epsilon. We have f of x here. Minus L, which is 1, minus 1. Let's start that again. 4x minus 1, 15, minus the 1 there, minus L. Should be less than epsilon. This gives us 4x minus 16, which is less than epsilon. And I'm going to factor a 4 out of that. And when I do that, I can actually take it out of the absolute value because the absolute value of 4 is 4. So we're good. And now I'm going to divide both sides by 4. All right, and this is my new delta. This is my delta. So for our proof purposes, our delta is going to be epsilon over 4. All right, next up, part 2. Step 2. So now we're doing this part of it, this here. So we're going to go if the absolute value of x minus 4 is going to be less than delta, which in our case is going to be epsilon over 4, then we're going to do this, and this should be less than epsilon. All right, so we now have this. And we know that this should be, we know that we have this statement here. And notice that's exactly 4 times that, which means this is going to be less than 4 times epsilon over 4, which is just epsilon, which is what we're trying to prove. Therefore, we have shown less than epsilon. This is getting into the nitty-gritty of mathematics, and most of you engineers, you're not going to run into this most likely, but for the math majors and so on, you're going to run into this kind of stuff often. We have one more to go. So we're going to prove that this limit is equal to 13. Now you'll notice if you plug in the 1 here, 8 times 1 is 8, 8 plus 5 is 13. So you're like, can we just prove it that way? No, this is the more precise definition. So let's do our step 1. Again, we're going to assume that epsilon is positive. I'm going to take f of x, which is 8x plus 5 in this case, minus L, which is 13 in this case. And so we're looking for our delta. And so this should be less than epsilon. This becomes 8x minus 8 less than epsilon. I'm going to factor an 8 out of that. And you notice x minus 1, there's our x minus 1 there. And here is our delta. Use delta equals epsilon over 8. And notice delta is dependent on epsilon, as it should be. Step 2. So we're going to say if the absolute value of x minus 1, there's the x minus 1 there, is less than delta, which means we're going to choose our delta to be here. Then the absolute value of f of x, which is 8x plus 5, minus L, which is 13 in this case. This needs to be less than epsilon. And we'll notice that this here, this is exactly 8 times that. So that's going to be 8 times that, less than epsilon over 8, which is just epsilon. Therefore, we've shown that f of x minus L is less than epsilon. I know that seems very convoluted, but it's interesting.